Hello, everybody. Thanks for joining us today. You're part of the 500 people worldwide who have registered to this webcast. This webcast, powered by iDash Macro News, will present the AI's impact on the automotive industry, its trends, market, and players. Before that, let me quickly introduce Yole group of companies. We provide marketing, technology, and strategy consulting, media and corporate finance services, reverse engineering and reverse costing services, as well as IP and patent analysis. My name is David Jordan. I'm part of the sales support and customer service of Yole Development. So before starting the presentation, let me give you some practical information. You have the possibility during all the webcasts to submit questions. To do so, you simply have to use the box at the bottom of the screen with the label Ask a Question. We will answer as many questions today as time allows us, and for the remaining questions, we will follow up with you via email. And concerning the materials and content of the presentation, please note that they are already available and downloadable in the resources section of the webcast platform. Furthermore, you will receive an email after the webcast with a link to the recorded session. We are pleased to welcome today Willard Tu, PhD and market analyst specialized in software and computing at Yole Development, as well as Willard Tu, senior director at Xilinx. Let's start the webcast presentation with Willard Tu. Willard, please.
Hello, thank you. Thank you very much, David. So let's start the presentation with first the scope of the webcast. Okay. Just to be clear on what we will talk about today, we will talk about artificial intelligence and its impact on automotive. Mainly on the computing, we will talk mainly about computing hardware and what we think about the next trends, the future, who are the players, supply chains. We'll talk a bit about revenues. And just to begin a bit, we will make a short definition of artificial intelligence, because in this world you can put whatever you want. It's in big hype since a few years now. And I want to clarify a bit about what we, at least for the webcast, include in artificial intelligence. So as you can see, there is the Wikipedia classical definition, and there is many ways to speak about artificial intelligence through the research goals, for example, with some of you maybe knows already, so like natural language processing, like motion and manipulation. We were talking about very soon about social intelligence, and one of the main domain obviously is learning. For that, since late 50s, mathematicians have used many tools to go to this artificial intelligence. These tools are search and optimization, logic, probabilistic methods, and maybe the most known use are classifiers, and some are most recent, the one that works the most are neural networks. And we often, because it's in the domain, we often linked neural networks and deep learning. Today, we will speak about deep learning. Okay? Let's continue. So artificial intelligence in automotive, we have two different segments. The first one is very famous. We were talking about autonomous driving. And in autonomous driving, there is two different worlds, the ADAS world and the robotic world. So I will go deeper in the details later. On another side, we have a driver environment, and particularly infotainment, with two different applications, which are gesture recognition and speech recognition. As we are talking about computing hardware, which is linked to artificial intelligence, there is two, let's say, trends in this computing hardware. One which is close to sensor, just behind the cameras, for example, or behind the microphones. We call it sensor edge computing. And the other one is something which is very powerful And it's like a computer inside the car, and we call it centralized edge computing. In this webcast, we will not talk about cloud computing. This is so large subject, but it deserves its own webcast by itself. So let's start with autonomy. In autonomy, there is 5 different ADAS levels, and these ADAS levels, sometimes the limits between these levels are very blurred. And when we talk about that, it needs, at least for this webcast, to be important to think about, to get the same definitions to all the people. Here are the definitions we have found are the best for us, for Yole to define and to create the segmentation related to artificial intelligence in automotive. So first, we have the 2 first levels with very few autonomy or no autonomy and very few autonomy, so 0 and 1. At level 2, we can speak about take the feet off, and level 3 hands off, level 4 eyes off, and level 5 mind off. Each kind of levels has its own entries, okay, and we'll speak a bit more about that on the next slides. But just to think about that, the strategies are different from traditional car makers like GM, Ford, Volkswagen, newcomers like Tesla and NIO, and robotic car players or tech giants like Google, like Uber, like Baidu, all these companies. So why? How it works? For autonomous vehicles, there is 2 distinctive paths to get to autonomous driving. The first one is the one used by traditional car makers to add functionalities following, for example, the Euro NCAP requirements to get the 5 stars. They are adding functionalities to get up in these levels. The more functionalities to get autonomous, to reach autonomy, you add you increase in the levels. So these guys are Toyota, Volkswagen, Nissan, Mercedes, and this is the traditional car makers, and they are going in this way from level 1 to level 2. We are talking now about level 2 plus level 3, level 4, and level 5. The other strategy is to directly tackle autonomous driving, and this is the way tech giants have chosen. So it works first in designated areas in limited distance. This is for robotaxis, because when we are talking about robotic vehicles, there is 2 different segments in robotic vehicles. There is the robotaxis and there is the shuttles or autonomous buses. And if we are talking in robotaxis, we are more thinking about areas, designated areas, and when we are talking about shuttles, it's more about low speeds and very close environment, like university, like hospital, like airports. But keep in mind, by both of the strategies end up at the same place, which is full autonomous driving. To do that, we need computing power. We need computing hardware. And on these slides, I'm trying to describe from level 1 to level 5 for each sensor the type of hardware you need to have to make it work. Let's look at level 1, for example, and we can imagine that behind ultrasonic sensors, the technology penetration for computing hardware is 100% MCU. Okay, what it means? It means that 100% of players have chosen to put a MCU behind ultrasonic sensors. For radars, we can have, in 90% of the case, we have a MCU, and in 10% of the case, we have FPGA. For forward camera, for level 1 again, same thing. 90% MCU, 10% are, in this case, is more what we call an ISP, okay? But just to do ACC, which is automatic cruise control, you don't need very powerful computation behind that. At level 2, it's a bit more complicated, and you can start to see some vision processors because you can have a fusion of cameras, the first fusion. We are talking about first fusion of cameras, and it's the beginning of understanding the environment around the car. And this can be done through a VP, a vision processor like the Mobileye IQ3 or a FPGA. I think we will see some Xilinx solution after this presentation, or let's say light fusion platform like Renesas R-Car H3. Level 3, well, level 3 is very complicated. And it's so complicated that not only some players have chosen to not go there, but we're expecting something this year, and it's not on the road today. But to do that, you have to think about fusions. It means fusion of cameras input, where you have to handle all the inputs from all the cameras to fuse it to understand the environment around the car. And to do that, you can use vision processor, but they are powerful vision processor like the Mobileye IQ4 or the Mobileye IQ5 that will be in 2 or 3 years. And the Renesas next generation or the first NVIDIA platform, okay? For level 4 or level 5, well, that's simple. You need so much power that you can only use fusion platform like in this NVIDIA solutions. And even with that, you will have to add sometimes some discrete GPU. You have to add FPGA for pre-processing. So it's very complicated yet. And well, there is no really good idea about how it will be in the future. Okay. So let's continue to slide 9. After seeing about the computing hardware suite, let's talk a bit about revenues. I will not enter in the detail there, but just something very, well, not intuitive at least. The thing is that when we look at revenues, the segment which will get the most of the revenues for artificial intelligence is robotic vehicles. Even if the volumes are low, actually the computing platforms are so expensive that it will get the most revenues. We are not talking about $50 or $100. We are talking about tens of $1,000 for this type of vehicles. And it is why we can see on these plots that robotic vehicles will get the most of the revenues for artificial intelligence computing hardware. On slide 10, this is something that it's very interesting. Actually, a lot of people are asking us, well, 2 things: power dissipation, performance. And we need to answer about, obviously, what is the best is, if you look at the plot, is the bottom right point. I mean, this plot, you need to read it from top to bottom and left to right. So if we look at this comparison chart, you will see that we can distinguish which platform is dedicated for. Processors for ADAS level 2 are below 1 TOPS of computation power, okay? On the other side, robotic vehicles are in the range of 100 TOPS. Even if it's still complicated, the next battleground of the ADAS industry, we think that it will be level 3. But for that, it should ask for a big jump in overall computing performance. And even if IQ4 seems okay for level 2+, we don't think that it will be enough for level 3. Same thing for the single Xavier, is fine for level 3, but we think that it's not probably enough for true level 4. Okay. If we talk about ecosystems, as I said at the beginning, there is 2 different worlds in autonomous driving: the robotics and the ADAS. This is again very important. 2 ecosystems, 2 supply chain, 2 prices, 2 different strategies. This is exactly not the same world. But in both of these ecosystems, we can see that the supply chain are organizing. And ADAS ecosystem are built around historical automotive OEMs, traditional car makers. And even if we see that sometimes, or maybe most of the times, computing hardware companies are directly talking to OEMs, and then OEMs told the tier ones to use this or this type of computing hardware. For the leader in this part of the market, we can see that Mobileye is a bit ahead, and but the competition is tough. maybe Texas Instruments and Toshiba, Ambarella, they have been taking some time to get in the place, but now we see that they are proposing some nice solutions. And since the beginning of the year, NVIDIA is proposing something for level 2+ and level 3. For the robotic vehicles ecosystems, the challenge is very, very difficult. And there is a lot of partnership. There is a lot of new startups getting in this world. There is a lot of different solutions. And I mean, NVIDIA, Apollo, they are proposing, they try to build an ecosystem for robotic vehicles around them, and it's working pretty well, actually. But the thing is that because it's so difficult, particularly in software, a lot of solutions have been made through open source, through simulation, through mapping. All these kind of techniques, methods have been shared a lot. Let's talk about infotainment a bit. For artificial intelligence in infotainment, there is 3 ways to see that. There is the driving data collection and smart maintenance. There is voice control or speech recognitions. There is gesture recognition. And if we go a bit in the detail, gesture recognition, I mean, I think you understand exactly what it means. It's if you want to change the control, if you want to change the station, you have just to make some gests in front of a camera, and if it recognizes it, it will, you can control what you want to do. For speech recognition, it's kind of the same thing you can have at home with OK Google or Alexa, but it's inside your car, and what you can do is change the destination, it change the music, it's open the door for your garage, whatever. For maintenance prediction, we will not talk a lot about that in this webcast because it's more on the cloud computing. It's not really what we want to put in this webcast. It's a bit different. What are the trends? So the trends from MCU to Fusion platform. Today, what we can see is that for infotainment, you don't really need a lot of computing power. However, if you put some gesture recognition into your car, you will need some kind of vision processor or even some fusion platform if you have multiple cameras in your cars. And there is 2 ways to do that. Either you use the computing platform used already for ADAS, or you have 2 different computing platforms. Actually, we think that this is the solution, just for safety reason, for security, for not hacking your ADAS car. Okay, I'm sure you don't want anybody to drive your car with a phone. So actually, we think that the way to implement artificial intelligence in the cockpit is to use a different platform from the ADAS one. If we talk a bit about prices, so it's average selling prices. Yeah, we are thinking about the fact that we will not see any gesture recognition or speech recognition in level 0 or level 1 car. It does not make sense to get a high-end car, a low-end car, sorry, with such functionalities. So here we think that we will see gesture recognition more from the level 2 to level 5, and between $20 to $30. So that includes sensor, computing hardware, and software. For speech recognitions, it will begin, let's say, around $8–10, and it will decrease with time to reach $4 to $7. If we talk about revenues, we see that level 3 ADAS, it is ADAS level 3 that will generate more revenues for AI for infotainment. That just makes sense because it's a question of volumes. We imagine that there will be much more ADAS level 3 in 2028 than today, for sure. There is 2 different strategies in infotainment. The first one is to get a generic and collaborative operating system like Android Auto, and you can adapt the user interface with it. The second strategy is to be a bit closed and to develop the platform by your own, by yourself. The thing is that most OEMs provide a seamless connection Bluetooth connection, to be clear, between the car and the smartphones, to get the connection first, the internet connection, and to provide advanced infotainment. But either some OEMs develop only basic infotainment application, and you use your phone to get other applications like phone call, voice assistance if you want to play music, or others, OEMs develop entirely and built in all the infotainment application. That means that at one point you can say, like you say, okay Google, you can say, hey Mercedes, or okay BMW in your car. This is a way to see the business model. If we look at the trends, there is one thing which is important, that it's kind of difficult to see any trends because there is a lot of players there, okay? And the thing is that there is who is taking the value. And today we can observe that there is conflicts between automotive players with big tech players when we start speaking about data, for example. And again, for infotainment, there is not any standard. There is many business models, there's many players from different fields, software, hardware, tier 1, tier 2, sensors. And this is still a mess. When we are talking about gesture recognition, there is a lot of people who want to get there, but the thing is that, is it really an added value to get gesture recognition in your car? Well, this is still a question we have to ask. And today there is no specific computing hardware for infotainment, for artificial intelligence. I mean, artificial intelligence, particularly for speech recognition, is limited. I mean, if you don't want to use the cloud computing, you can't do, at least for now, speech recognition. There is no supply chain. Many players, as I said, are competing. And one thing which is very important is that if you want to play in this place, you have to get your hardware qualified for infotainment for automotive, which is not something very easy to get. So let's go to the conclusion. Today, autonomous driving, it's in a hype, okay? We have many articles each day on that, and this is great. If we look at investments, the last 4 years, we reached $80 billion. The revenues in 2018 for computing hardware for artificial intelligence reached 156 million. So the difference is still huge. If we look at the total semiconductor market, again, automotive semiconductor market is very low, and AI-related application much more than that. But the thing is that this will explode for sure. Artificial intelligence in automotive is inevitable, and this will grow exponentially for sure. There is, if we want to understand the value flow of artificial intelligence, or not only artificial intelligence, but more about autonomous driving, there is 4 kinds of different business models. There is obviously the car manufacturer, the OEM. There is the car electrification company. So for the batteries, if we are talking about electric cars, which is what we, when we speak about autonomous driving or robotaxis or shuttle, this is the case. There is the guys that are making the hardware and the software, so the brain of the car, autonomous driving itself. And there is the service provider, so like the Uber, the Lyft, the Google Waymo, that you have to get an app to use this type of cars. And what we see is that the major value flow will go to the service provider, and it is why we are beginning to see even some OEMs go there. There is some services in Singapore proposed by BMW, for example, to get a taxi, a BMW taxi. Okay, and we think that this will be the trends that OEMs will slightly change or add to their business model the service to get robotaxis or shuttle. But if we look at who is the winner, I mean, this is kind of easy. Why that? If we look at what Google is doing, it's at least it's great. At the end, I'm writing at the end, Google's take it all, but yes, why that? The thing is that they already have something in homes with OK Google. I remind you that, I think you know that, but the Google business is to get data. So each time you are talking, they want to do exactly what you are doing at each minute. It's they are not Big Brother, but they are kind of want to know what you do to sell your data, to sell you ads. And okay, let's continue about. Let's come back to the subject. If we are talking about what they are doing in your home, we have the virtual assistants with the OK Google. They are building the robot taxis, so they will be able to know what you are doing outside your home. And they have all the tools to know that with the software, with Android Auto. They have the Android on smartphones too. And they have the tools, the physical tools with data center and hardware. They have built the TPU, so the tensor processing unit to analyze all this data they gather. If I conclude rapidly on some points, so leaders, the main information of that, leaders, Intel Mobileye for ADAS vehicles, but the competition is tough. For NVIDIA, for robotic vehicles, and there is little competition. Maybe some ASIC startups will go in the place, but in a few years. For trends, ADAS, as I say, ADAS vehicles, they are adding more and more functionalities, where robotics vehicles follow two trends, with robotaxi on one side and low-speed shuttles on another side. In terms of numbers, we're talking about a total market of 15.5 billion in 28, and AI represents 90% of this revenue, so it's quite huge. I will not read all the numbers. Keep that for you and take the time to read it. For the value flow of autonomous driving, we have 4 types of players that share this value flow: the car OEMs, the car electrification companies, the computing hardware companies, and finally the tech giants that take these value flows, okay? Particularly Google, as I showed just before. Finally, if we are looking into the future, the stakes are huge, because autonomous driving is a market that for sure will grow and at a high pace, okay? Therefore, you need to understand that why that? I mean, why we are so sure that there will be autonomous driving? Because autonomous driving resolves at least 4 problems. Safety problems. It's an easy service when we are talking about service in cities, for example. Traffic problems and pollutions. Robotic vehicles will be the major market revenue generator, as I say, because of its need for high-end components in terms of sensors and in terms of computing. They want to be agnostic in this segment. And finally, and this is a bet we have internally, we think that the first ADAS level 5s, so for Mr. Everybody, the first autonomous driving car will hit the road in 2030. Thank you very much.
Thank you very much, Johan, for this interesting presentation. We will now continue with Willard Tu, who will present Xilinx's vision of the AI for automotive market. Willard, the floor is yours.
Thank you very much, and good morning to those in California, and good evening to those in Europe. So today, I want to talk about the challenges that the chip makers are facing to support autonomous driving and the AI movement in automotive today. There's certainly a need as we look forward for what we consider adaptive silicon solutions, and I'll share really 6 reasons why we feel there's a need for adaptability. So the next 2 slides I want to share really are kind of to set the stage, and Johan had covered some of these items already, but I'm going to kind of review them quickly here. So clearly there's 2 paths to autonomous vehicles. We consider, if you look at the diagram here in the yellow blocks, what you see on the left is the more incremental approach that we think the traditional tier 1s and OEMs are going to follow. And then on the right side, what we see here is more the moonshot approach, where some of the newcomers in the marketplace that are coming, they're directly going to autonomy, and so it has a different approach. And at the bottom of this diagram, you can see some of the fundamental technologies that are involved in cameras, LIDARs, and 4D imaging radar. And actually, Xilinx, we actually enjoy quite a bit of business in this particular space. We do quite well in all the sense technologies. And then on the left, you'll see a couple of ADAS domain controllers like surround view or in-cabin monitoring, which would include driver monitoring systems. Again, areas that Xilinx does very well. And then on the very far right side, you'll see a little block diagram, which is really a simple example of a autonomous driving domain architecture. There's 4 compute blocks in there. And in the compute blocks, you'll see one is what we call DAPD. And I'll talk a little bit more about that. And then there's also a compute accelerator where all the AI is done. There's a serial processor, and there's a safety micro, typically an Infineon Oryx device. Okay, so as we look forward, the one thing I want to emphasize throughout this is that there's really a great divide here in terms of electronics nowadays. The difference has really been in the past, electronics was more about command and control. It was a lot simpler electronics. Everything was standard. So we had a standard approach. When we had a standard approach, we had a lot of volume, and then there would be the effort to cost optimize. And with ADAS and AD right now, that movement has changed quite a bit. It's much more complex. There is no one way to solve the problem. And in the approaches that are being done, many of them have like different types of interfaces. And again, the volume is very fragmented and very low. So this creates a lot of challenges for silicon vendors because silicon vendors, at the end of the day, really, really want to have high volume. They love, the mobile market because it ships 1 billion units a year. And automotive, at 100% implementation of like a powertrain, would reach, in the areas of 100 million. So you can see there's an order of magnitude difference in those type of numbers. And clearly, when you look at body electronics or powertrain electronics versus ADAS and AD, there's another big gap in terms of volume. So I talked about kind of one of the number one needs for why you need adaptive silicon is really comes down to scalability and flexibility. And I talked about this central compute for autonomous driving and these 4 compute blocks that we see in here in the center gray box. And the reason why this is important that we need to have this function called DAPD, which we call data aggregation, pre-processing, distribution, where Xilinx plays a very important role, is that really, if you think about it, all the autonomous driving efforts that are going on today, they're all different. Nobody's using the same number of cameras. Nobody's using the same number of radars or the same number of LIDARs. They all have different sensor configurations. And at the same time, those sensors all have potentially different capabilities. A good example of the different capabilities is some people could use a simple 2D radar, where somebody could do a 4D imaging radar, and those would have different types of output. The 2D radar would typically use a CAN-based output because you're transmitting object-oriented data, whereas a 4D imaging radar or LIDAR is going to output a point cloud, which has a lot more data. So these are challenges, and I think having the what we call the plumbing station, where we have the DAPD capability, we can vary the different types of pipes, whether they're copper, PVC, or steel, and then also we can vary the bandwidth, which would be the diameter of those pipes. So it's really important to recognize that there's just no one way to do it, and that's why a FPGA type technology is a perfect fit for the data aggregation pre-processing. And of course, we still play very strongly in compute acceleration, as do a lot of companies who are all pursuing the AI engine. Everybody wants to be in the AI engine. This is the sexy part of the business. But again, we see that adaptability will come into play here as well, and I'll talk a little bit later about that in terms of the AI aspect of it. So the next 2 slides I'm going to kind of cover, it just kind of re-emphasize this point of adaptability and scalability using interfaces as an example. So the next slide here shows the Infineon HSSL interface. What Xilinx has done is we've worked with Infineon. We saw that Infineon was very present in many of the ADAS and AD systems, and we thought, well, why don't we collaborate with them a little bit more? And they have a custom interface that they have, high-speed serial link, and what we did was we worked with a contractor, Xylon, to implement this in FPGA Fabric. And so this is available to the market, and you can implement then the HSL interface in our FPGA Fabric, giving you the ability to communicate between the FPGA and the Infineon Orex MCU at a higher data rate. And this is certainly an advantage at the system level for the designers. So this is just one example where we have the flexibility of creating our own custom interfaces inside the device. Another example is MIPI. So obviously there's a lot of MIPI interfaces being utilized, and the standard changes from time to time. An example of that is in 2018, where we were able to achieve a data rate of 1.26, and then the subsequent implementations have now sped up to 2.5 gigabits per second. And if you were an SoC vendor that did a traditional hardened approach, not utilizing FPGA technology, you would have to take 2 years to meet that standard, to introduce that new standard to the market. Whereas with, again, FPGA technology, we're able to adapt to that right away, the same way we did with HSSL. We can create that in Fabric, what we call FPGA Fabric, and implement that immediately so that the system developers can take advantage of the latest standards. So those are just two examples where the flexibility comes into play. Now I'm going to kind of switch gears a little bit and say, well, why is adaptive silicon good, and for example, in the LIDAR market? And the reason why it's very relevant here in the space that we do very well, again, is there's no convergence. There's no standard way. And you can see on this chart from Yole, there's many different approaches in LIDAR today, and you can see that there's probably easily 20 companies represented here on this chart, and I'm sure there's many, many more that this is an old chart from Yole, but I'm sure the latest one will have maybe 20 more. And the challenges here, again, is that they all have a different capability, they all have a different approach, and they may have different interfaces. And with all these differences, that just means the market is fragmented and the volumes are very low. And so, again, this is a value that we bring, that not one size can fit all, but an FPGA is like having a blank sheet of paper for the designer, and he can customize the FPGA fabric to what they need. And so our devices certainly fit this particular market need right now, which is fantastic. So the third reason for the need for adaptability really comes, an obvious thing, is changing requirements. And the best example of this is really the NCAP, Euro NCAP roadmap. This is not a static roadmap. It is something that's ever changing and evolving. It's very dynamic. And you can see where the NCAP organization is pushing for excellence. They're not saying, hey, you're done when you introduce AEB. They want to see AEB evolve to be perfect. And in doing that, you can see they have implementations of AEB where it started out where it was just really the head-on use case, and then they added the pedestrian crosswalk, the vulnerable road user. So you can see how automatic emergency braking has evolved over time. So changing requirements is another driving force to why you need adaptive silicon to meet the needs. You can imagine, again, a silicon provider who has a hardened approach, a fixed approach, will introduce a chip, and by the time he brings it to market, it may not meet the needs of the market any longer because the market requirements have changed. Forward-looking camera just happens to be a perfect example of that. Xilinx has enjoyed being in 3 generations, and we're planning to be in our 4th generation. And you can see where our ability to adapt to the change requirements has helped us maintain our leadership in this particular space. In fact, one of our customers is in production today with what we call our Gen 3, our MPSoC product, and they are able to generate 2 generations of product with one device. So that just, again, exemplifies the flexibility and adaptability of our solution. Okay, so the fourth reason, I think the backdrop of this whole theme is the AI explosion that we see. And again, this is an area that Xilinx does very well in. We are the AI inference leader, and the reason for that is the adaptability. AI inference is pushing the limits of the industry. As a silicon provider, we're not in a situation where all silicon providers can solve the problem by just coming up with new silicon. That's why AI has come to the forefront. What we can see is some of the technology trends that have been driving the silicon industry for years are no longer able to push and solve the problem by themselves. We need to solve it with AI. So example here is Amdahl's law, where you can increase your performance by adding more CPU cores. You can see that now there's a lot of octa-cores solutions in the mobile space. Maybe they'll go into 16-core implementations. That's certainly a possibility. But at a certain point, that's going to start hitting an asymptote, and you're not going to get your economies of scale any longer. And of course, Dennard's scaling and Moore's law are telling us, look, it isn't that we're getting twice the capability at half the price. That's not happening any longer. So why do we need AI? AI is less demanding on the overall silicon processes needs. And so as we look to evolve to more neural net approaches, it doesn't put as much pressure on the silicon guys. Now, let's get a little bit more involved in what's going on in the silicon space. In this particular case, what I'm showing is an algorithm that would be used to identify a dog. And as you can imagine, this algorithm has now become what we call a domain-specific architecture. We believe that really you need a special combination of hardware and software to achieve the outcome. And so here we see that you might have custom data paths, you might have certain types of precision or memory configurations. Next slide. And those all help define what is a domain-specific architecture. So going back to the dog example, you can see over time, over the last 6 years, we've had implementations. Sorry, let me step back here. We've had implementations where AlexNet, for example, was less than 60% success rate, and now you see some neural nets are able to achieve 80+ accuracy. So things have changed in a short matter of time. So imagine if you based a silicon solution on the early solutions that happened. By the time you come to market, you may not be the best in class. So that's one of the challenges that the AI market has imposed on the market right now. So just some illustrations here of how AI is evolving incredibly fast. And again, the key point here is the silicon hardware design cycle can't keep up with the rate of AI innovation. Let me just page through some of this animation. So the fifth reason why we think that you need for adaptive silicon is really the data pipelining for AI. And if you take a look at a lot of silicon architectures out there, the traditional CPU, GPU, and DSPs, they all call for what we call batch processing. They're all serial architectures that the only way you can push data through is you have to clock the architecture very fast. And what ends up happening is as you batch the data, you introduce latency. So here in this example, you're going to see, let's say, 4 independent frames coming from a single camera. And so you can see here in this example here, the data is going to accumulate, the 4 data inputs are going to come in, and then they're going to be processed at the same time, giving you all 4 resultants at the same time. But you had to wait for that batching to accumulate before you processed all that data. In the case of having a much more adaptive silicon approach, like an FPGA, we're able to pipeline the data flow so that as an input comes in, it gets processed immediately, and it exits out and gives you the result. And the next input comes in, and subsequently, we're reducing the latency that's involved. And so you're here in this example here, we said, hey, it definitely could affect the braking distance of an automatic emergency braking system, so that you have a much lower latency. So that's the 5th reason why we think there's a need for adaptive silicon, is the data pipelining. And this slide here just kind of gives you an example of where latency and AI have kind of converged, and two success cases for Xilinx. One was the Daimler MBUX interior assistant, where they're using the gesture recognition, using a neural net capability. And if you see here in the quote from Daimler, they picked Xilinx because we were the lowest power, the lowest latency for AI, and we're very proud of that. And on the flip side here, we've got the ZF guys working with us both on the more domain controller for autonomous driving. They're using us in a DAPD role because there's a motherboard here at the very bottom which uses a DAPD, and then you can see they have 3 compute tiles which they could populate with Xilinx solutions for AI. So those are great examples of where we had some success with adaptive silicon. So now I'm going to give you kind of the 6 reasons why we think we have a competitive advantage in this marketplace. And it's kind of a rule-changing, a game-changing technology, which we call dynamic function exchange. And what that means is we can take a number of features and bundle them into mutually exclusive groups. So in this particular example here, I've looked at in-cabin sensing here, and I have what I call a pre-drive mode, a drive mode, and a post-drive mode. And what happens is we can then take all those algorithms in the pre-drive mode, which could be a keyless entry, a interior or exterior parameter sensing, or biometric identification, and all those can be loaded into the device and then implemented. Once they're done and you've now switched to drive mode, we would take those functionality out of the device and then load in this hardware needed to implement driver monitoring systems, maybe emergency passenger safety algorithms, maybe a advanced restraints controller, to kind of using the pose estimation to figure out where the driver and passengers are positioned to optimize the airbag deployment. And then, of course, I talked about the MBUX interior assistant. You could do gesture recognition. And then as you leave and you leave the vehicle, you're in now post-drive mode. You can do all those detections that we talk about that are, involving infant left behind or pet left behind, or even your laptop or your sunglasses or your wallet. All those things become very relevant. So this is a good example, and you can kind of see a more simplistic diagram up into the right here, where I show a bunch of color tiles, each of those represent a function. Either you could have an Uber chip that can do it all, or you have to have multiple chips representing each color, or you can do this dynamic function exchange where you can rotate in functionality. A couple examples where we see the use of dynamic function exchange are, we see that the opportunity is in using front camera and surround view in the same device, and or we've seen several of the LIDAR and 4D radar guys talk about making their radar, instead of having one that's short range and one that's long range, they can then configure their sensor unit to be long range or short range, so they only have to sell one device, but use speed as the context to switch. So that really kind of concludes my presentation. I think in summary, you can see there's 6 reasons here. Again, ADAS and AD is evolving too rapidly. It's very difficult to hit a moving target if you think about it. The industry has not converged on a common approach. The Euro NCAP guys are just pushing for continuous innovation and continuous improvement. And you can see where AI explosion is bringing about a lot of change. Flexibility in the data pipeline to achieve low latency. And we think the industry needs more versatility with dynamic function exchange, not always demanding that we have to have more and more performance. If we partition the system properly, we can actually achieve a lot more functionality with less performance. So that's the conclusion. We need adaptive silicon. I hope you guys are going to look into utilizing more FPGA technologies in your ADAS and your AD systems.
Thank you, Willard, and thank you all for this relevant presentation. We are now going to wrap up with a Q&A session. We will answer as many questions today as we can, and we will follow up via email for all the remaining questions. So let's begin with one question for Johan. What are the ways to get the autonomous driving faster?
Okay, so to get to autonomous driving faster, there is 2 ways. The first one is, to drive, to get miles, more miles. This is a way to put your car on the road and to let it drive during 1 year, 2 years, 3 years to accumulate data, to make analysis of this data. This is one way. I think there is another way, which is simulation, and this is something very interesting with simulations, that now you can do so realistic simulations that you can almost test the autonomous driving software directly with this simulation. So that's great. So what is the way? I think there is two ways, and you should use both of these ways.
I think those are excellent suggestions. I would actually take a little bit different answer with that. What I see in the marketplace is, I think, a lot of reinvention of the same functionality over and over again for cost reasons. And I think we're in a phase right now in the industry where it's completely different to think about, like I said before, body electronic versus ADAS. If we're innovating or we're dedicating resources to reduce cost in a time frame when we're all about innovation, reinventing a functionality like a front camera, it's just kind of wasting time. I mean, there's very limited resources available to the engineering guys today. And if we're spending that valuable resource to save $1 or a penny, it's not going to help the problem. We need to focus it on innovation, and simulation and all these other cases are certainly things that need to happen. But the engineering resources is a limitation today in the marketplace.
Okay, thank you. We have some question about Tesla, their strategy, their technologies. Can you talk a bit about that?
Do you want to start about that, Will, or do you want me to
unfortunately,
talk about?
I'm probably not going to have a lot of color to add on this. I don't own a Tesla. I haven't experienced the system. I know they've made a lot of claims, and it's hard for me to really comment on those claims if I haven't personally experienced the system.
Oh, I think that there was questions about the silicon. You know, their new chip. What do you think about the chip? I mean, I'm actually a bit like you, but I think that there is a lot of announcements from Tesla, and the way I'm seeing that is let them get a bit of time. So for the question that if traditional car makers will make their own chip, I don't think so. I mean, Tesla is a very particular company, and I'm not sure that traditional car makers will will transform themselves into a silicon company. I don't think so.
Well, let me add to that a little bit. I mean, the one thing I mentioned earlier is that silicon vendors need volume to amortize the huge R&D cost to create a solution. I mean, we're talking, $1 billion to come out with a complex chip sometimes. And if you imagine, if you're amortizing $1 billion over 500,000 units, that's just going to make the cost very, very high. And so I think that's where I look at it. I mean, that's where the silicon vendors really need to have that volume, and Tesla by themselves just don't generate that kind of volume.
Yeah, I completely agree.
Right. Now let's come to Willard. We have two questions for you. First question, what are the top challenges Tier 1s and OEM facing when it comes to ADAS and AD development?
Yeah, so I think I kind of covered one of them already, the limited resources. That's one thing. Time to market. I mean, we can see an incredible pressure on time. I mean, I've never seen it where engineering guys are asking us every day, we need your help, we need silicon solutions. So there's a lot of pressure, and I think that pressure is coming from people like Tesla who create a dialogue or narrative that suggests that the technology is very reachable. And so everybody's trying to play catch up. Everybody wants to push the envelope. And then the third reason is the investment of capital. You can see in some recent news of companies like Cruise and Argo and Waymo, they have very deep pockets, and they're spending probably billions of dollars a year to drive for these solutions, which makes it a situation where more companies either have to join together to fund this type of effort, or they have to have very, very deep pockets or go access government money or venture capital. So the amount of money it takes to accelerate this, to hire the right resources and to push the ability to innovate faster, all those things are really the challenges I see right now. There's a lack of skill sets in the neural net area. I don't think the universities have pumped out enough really good engineers that are able to address neural nets, but I think it's all coming. So I'm very optimistic of the future. Having experienced a few robotaxi rides myself, I think once you've been in a ride, you see the potential that it's certainly, the technology is very, very close. It's there. It's a matter of making it better, more robust, and making the affordability come down.
All right, one last question for you, Will. Do you consider driver monitoring for ADAS, infotainment, or command and control?
That's a really good question. Actually, most of the driver monitoring systems that our customers have been involved with, we've seen that is really wants to be a standalone function right now. I think that's mainly for functional safety reasons. They don't want to have conflict with another system, whether it be an infotainment or a cluster. Now, it doesn't mean that you're not seeing driver monitoring systems go into clusters and infotainment, but then there needs to be special attention to sandbox that functionality away from any interference from the other applications that might be running on the same processor. So I think right now the majority of the solutions are out there are dedicated solutions, and we think that it's probably better to do that way for functional safety reasons, but I think in time those functionalities will evolve into domain controller. I talked about dynamic function exchange. I think there's no reason why you can't run it on another device, as I suggested, maybe swapping in and swapping out a function if necessary. But I think it will get integrated at some point in time.
Right. Thank you very much, Will. So the webcast is ending. Within the next 40 hours, you will receive an email that will include the recorded session. Also, please feel free to share this presentation with colleagues or anyone that can benefit from them. Let me remind you that you will find all the information about our reports and monitors on our website, i-markernews.com. Do not hesitate to contact us if you have additional questions. You can find the appropriate contact on the last slide of the presentation. Thanks a lot for joining us today, and have all a good day. Thank you very much.
Thank you very much. Thank you.